Let's look at temperature. We have three goals. We want to relate temperature to the energy of molecules. We want to look at temperature readings and convert from Fahrenheit to Celsius to Kelvins. We're also going to relate a heat to energy transfer. We'll answer some questions like what is theoretically the coldest possible temperature out there, and where do we find it in the universe? Temperature is defined as the average kinetic energy of the particles in an object. Let's review. Kinetic energy is energy due to motion. Potential energy was energy due to position, but we're focused on kinetic energy, energy due to motion. Here we have two boxes that contain 20 particles each. In the left box, the particles are traveling at a certain speed, but in the right box, we use longer arrows to show that they're traveling at a faster speed. So let's see which one has a higher, represents having a higher temperature. The left box, the right box, or do they have the same? It is the right box that has a higher temperature because the particles are moving faster. So we see that temperature depends on the particle movement. It won't depend on the number of particles. Let's look at how a thermometer works. First, a thermometer contains a bulb with a tube on it, and we place in it an alcohol. It's a red-colored alcohol. Above that red-colored alcohol is a vacuum, meaning there's no air. If we take the thermometer and put it in a hot liquid, which is what we see in the left side of the diagram, heat energy from the hot liquid is transferred into the bulb and the alcohol particles start to move faster. As they move faster, they move farther apart, and so the liquid expands and moves up the tube. This shows us that it's at a higher temperature. We'll consider three scales in which we can look at the temperatures and compare them: the Fahrenheit, Celsius, and Kelvin scale. Let's look at two important reference points, the freezing point of water and the boiling point of water. First, on the Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit. Then on the Celsius scale, the freezing point of water is 0 degrees Celsius, and the boiling point of water is 100 degrees Celsius. We'll look at the Kelvin scale in a little bit. Let's look at the difference between the boiling point of water and the freezing point of water on each of the scales. In the Fahrenheit scale, the boiling point is 212 minus the freezing point, which is 32 degrees Fahrenheit, and so the difference is 180 degrees Fahrenheit. Let's look at the Celsius scale. The boiling point is 100 degrees Celsius, the freezing point is 0 degrees Celsius. When we subtract these two numbers, on the Celsius scale, the difference between the boiling point and freezing point of water is 100 degrees Celsius. We'll look at kelvins later. But let's look at the number of dashes or lines that would be between the freezing point and boiling point on each of these scales. In the Fahrenheit scale, we have 180 dashes. In the Celsius scale, we have 100. And so let's consider the ratio. If we take 180 divided by 100, what does it simplify down to? We could say it simplifies to 9/5, or we could say on the fractions, or we could simplify it on the decimal scale to 1.8. And this contributes to the equation that converts between Celsius and Fahrenheit. We can convert from Celsius to Fahrenheit by taking 1.8 times the degrees in Celsius plus 32, and that gives us the temperature in Fahrenheit. We can also rearrange this equation and use Fahrenheit temperature to determine temperature in Celsius. And so the temperature in Celsius can be calculated by taking the temperature in Fahrenheit minus 32, we need to do those in parentheses, and then divided by 1.8. Next, let's compare them to the Kelvin scale. The Kelvin scale was determined through experimentation. What they wanted to do is find what would be theoretically the coldest possible temperature, and they called that 0. And then they classified the freezing point of water as 273.15 kelvins, and the boiling point of water was 373.15 kelvins. If we subtract those two numbers, the boiling point and freezing point of water on the Kelvin scale, we get 100 degrees Kelvin. That means there's the same number of dashes on the Kelvin scale as on the Celsius scale, and that's going to make the conversion much easier. So we can determine the temperature in kelvins by taking the temperature in Celsius and adding 273 to it. Let's practice some temperature conversions. The melting point of gold is 1064 degrees Celsius, and let's convert this to Fahrenheit and kelvins. When we convert it to temperature in Fahrenheit, we take 1.8 times temperature in Celsius plus 32, and then that means we take 1.8 times 1064 in parentheses, add 32 to it, and our answer is 1947 Fahrenheit. When we convert this temperature to kelvins, temperature in kelvins can be calculated by taking the temperature in Celsius plus 273. So we'll take the temperature in Celsius, which is 1064, add 273 to it, and we get 1337 kelvins. The melting point of gold is 1064 degrees Celsius, which means 1947 degrees Fahrenheit, and it means 1337 kelvins. Let's try another calculation. The coldest recorded temperature in Denver was negative 29 degrees Celsius, and it occurred in 1990. We'll convert to Fahrenheit. The temperature in Fahrenheit is equal to 1.8 times temperature in Celsius plus 32, so we will take 1.8 times negative 29 in parentheses plus 32. 1.8 times negative 29 is negative 52.2, and then we add 32 to it, and our answer is negative 20.2 degrees Fahrenheit. We calculate the temperature in kelvins by taking the temperature in Celsius plus 273. So the temperature in kelvins will be equal to negative 29 plus 273, and we get 244 kelvins. This means the coldest recorded temperature in Denver was negative 29 degrees Celsius, which is the same thing as negative 20.2 degrees Fahrenheit, and the same as 244 kelvins. Let's try one more calculation. The boiling point of the element neon is 27 kelvins. And let's express this in degrees Celsius. We know the temperature in kelvins is equal to the temperature in Celsius plus 273, but we want to convert from kelvins to Celsius. So we need to rearrange this equation. We need to subtract 273 from both sides. And so when we rearrange it, we say the temperature in Celsius will be equal to the temperature in kelvins minus 273. So we will take 27 minus 273, and our answer is negative 246 degrees Celsius. So the boiling point of neon is 27 kelvins, or which means the same thing as negative 246 degrees Celsius. When do we have negative Kelvin measurements? 0 kelvins is the coldest possible temperature. There is no negative temperature scale in kelvins. This coldest possible temperature is called absolute zero. It is 0 kelvins. It is the temperature at which an object's energy is minimal. Where do we get this temperature? It's impossible. You cannot have 0 kelvins. What is outer space? It's approximately 1 Kelvin because there's still microwaves out there. What's the coldest possible temperature we've gotten in a lab? It's approximately 1/billionth of a Kelvin, but we cannot reach 0 kelvins. It's impossible. And as we approach it, what happens is the atoms combine together to make one atom that acts more like a wave. We've defined temperature as the average kinetic energy of the particles in an object. Let's look at thermal energy. Thermal energy is the total kinetic energy of all the particles in an object. Temperature is the average kinetic energy, and temperature depends on how fast the particles are moving. Thermal energy is the total kinetic energy. So it's going to depend on the temperature because fast-moving particles are going to have a lot more kinetic energy. What else does it depend on? Here we have 2 boxes. The left box has 10 particles, the right box has 20 particles. Notice they have the same length of the arrow, which represents them traveling at the same speed. Which one has more thermal energy, more total kinetic energy? Is it the box on the left, the box on the right, or are they the same? The total kinetic energy is going to be greater for the box on the right. And this tells us that thermal energy depends on temperature, which is the particle movement, and it depends on mass, which is the number of particles. We've defined temperature as the average kinetic energy of particles in an object. Thermal energy is the total kinetic energy of the particles in an object, but let's now define heat. Heat is the energy transferred between objects at different temperatures. So heat is not the same as thermal energy, and it is not the same as temperature. Heat, energy transferred, it always goes from the object at a higher temperature to the object at a lower temperature until the temperatures are equal. And in this diagram, we see box A and B. A is red, which represents a higher temperature than B. When we let them touch, the energy is transferred from box A to box B, from the higher temperature to the lower temperature, until they have the same temperature, which is represented by the purple boxes. Heat is defined as the amount of energy that is transferred. So let's look at energy transfer. We're going to describe and give examples of energy transfer by conduction, convection, radiation, and then we'll also look at the difference between thermal conductors as well as thermal insulators. In this section, we will focus on the types of heat transfer, thermal energy. The types of heat transfer include conduction, convection, and radiation. First, let's look at conduction. Conduction is the transfer of thermal energy as particles collide. Since it requires particles and the particles must collide, it requires physical contact. And conduction can occur in solids and liquids and gases, but not in a vacuum. Conduction cannot occur in a vacuum because a vacuum is empty space. It lacks particles. Let's look at how conduction occurs. Conduction occurs when high-energy particles collide with low-energy particles and causing them to vibrate faster. In this diagram, we see a solid. Remember, a solid has particles that vibrate in place. The solid particles cannot flow past each other. And in this diagram on the left side, we see that heat is being added to one of those particles. As heat continues to be added to this particle, it vibrates faster and faster, and those high-energy particles collide with the low-energy particles, causing them to vibrate faster. Let's look at some examples with conduction. Here we have a pan that is sitting on a flame, and let's assume that that pan has hot water in it that's boiling. One example of conduction is when you touch the metal on a hot pan, the high energy particles of the metal transfers its energy into your hands, making the particles in your hand vibrate faster, and so we see conduction from a solid. What if that hot pan has boiling water in it? When you stick your hand in boiling water, there's physical contact, and the particles in the water are fast moving, and so they make the particles in your hand move faster also. What if you take the pan off and you stick your hand in the hot air above the flame? The hot air has particles that are moving fast. They collide with your hand and make the molecules and the particles in your hand move faster also. So conduction can occur in a solid, in a liquid, or in a gas, but it cannot occur in a vacuum. Solids are good conductors of heat. Which types of solids are better than others? Let's compare metals and nonmetals. A metal like a steel pan versus a non-metal solid like glass. Metals are good thermal conductors because they have freely moving electrons. Back in chemistry, we learned that metals have less than 4 valence electrons, and metals are constantly trying to get rid of their electrons to be stable. So a piece of metal has positively charged atoms in a sea of mobile electrons. Metals are good thermal conductors because they have freely moving electrons that allow the heat energy to pass. Glass is made of nonmetals. Nonmetals are atoms that have between 4 and 8 valence electrons. To be stable, they need 8 valence electrons. So 2 atoms share electrons to become stable and have a full valence shell. Electrons in a nonmetal like glass are not free moving. They are not shared among many atoms. As a result, glass, which contains nonmetals, is a poor thermal conductor. Heat transfer can occur by conduction, convection, and radiation. Convection is the transfer of thermal energy by the movement of fluids with different temperatures. A fluid is a substance that can slide around and past each other. Liquids and gases are fluids because they can move around. Solids are not fluids because solids have particles that vibrate in place, but those particles cannot slide past each other. So convection can occur in liquids and gases, but not in solids because solids do not flow, and not in a vacuum because a vacuum does not have a particle. An example would be like the movement of warm air above the fire. How does convection occur? When you have a fire, the fire warms the air directly above it, and as that air warms, the particles move faster and they move farther apart. As a result, they become less dense. The warm air rises due to its decreased density, and cool air replaces the warm air. As a result, it creates a convection current in which warm air rises and cool air replaces that warm air. Radiation is the transfer of energy by electromagnetic or light waves. There are many forms of electromagnetic waves. It includes infrared, ultraviolet, visible light, X-rays, gamma rays, microwaves, and even radio waves. Radiation can occur in solids and liquids and gases and in vacuums because radiation does not require particles. An example would be like sun shining on the earth. There's empty space between the sun and the earth, and the sunlight can still get to the earth. Let's look at how heat transfer by radiation occurs. The type of radiation that is associated with heat is infrared light. So energy is transferred by infrared waves and is absorbed by an object, and that causes the particles to move faster. And this is how the sun warms up the earth. Our goal in this section was to look at the types of heat transfer, conduction, convection, radiation, and to identify which substances are good thermal conductors and which ones are insulators.